Hi guys, welcome back to our channel Unknown IITians. Today in this session we are going to learn what are polynomials. Okay? So first we are going to discuss what is polynomial, the degree of a polynomial, algebra of polynomial, characterization of graphs, zeros of a polynomial function, identification of zeros and their multiplicities, graphical behavior and turning points in the graph. So now let's get started. Firstly, what is a polynomial? Polynomial is a mathematical expression which is sum of several mathematical terms. So, polynomial can be expressed as collection of several mathematical terms. Okay? So, each term in this expression is termed as a monomial. The term can be a number, a variable, or product of several variables. So that means polynomial, let's say polynomial is an x power n plus an minus 1 x power n minus 1 and so on a naught. So each term, this single term is known as a monomial. Okay. So basically we can say polynomial is a collection of several monomials. So a monomial can be a number. It can be a naught, or it can be an x power n, or it can be an x power n and y power n. So here there are two variables. So basically polynomial can be a number, a variable, or product of several variables. So that is the basic definition of a polynomial. So here in the given expression, here we consider the term am x power n. So here x is termed to be a variable. A power am is the coefficient. Okay, the coefficient is a constant term to which we are with which we are multiplying the variable, and here m is termed as the exponent. Okay, that is a basic polynomial. Next, we have some different types of polynomials. Polynomials in one variable, polynomials in two variables, polynomials in more than two variables. So, as we have discussed before, is an x power n. This x is a variable. Okay. Now, here polynomial with single variable means, now let us write a polynomial x power 4 3x square plus 2x plus 1. So here we have only x as the variable. No other variable is included in this polynomial expression. So that's why this is an example of polynomial with single variable. Basically, polynomial in one variable means the polynomial will contain only one variable. It may be x, it may be y, it may be z, it may be anything, but it will contain only one. Then next, coming to polynomial in two variables. So let's write an example. X square plus y square plus x power 4 plus y power 4. So here we are having two variables x and y. So this is a polynomial function in two variables. What if we have more than two variables? Let's write an example. X cube plus y cube plus z cube. So now here we are having three different variables. One is x, other one is y, and other one is z. So basically these are types of polynomials. Polynomial with single variable. So now let's discuss the degree of a polynomial. What is degree of a polynomial? The exponent on a variable in a term is called degree of the polynomial. So for example, we have discussed before, we are given a term an x power n. So this exponent of the variable is termed as the degree. Okay. Next, this is in a case where there is only one variable. But for example, if you are having multiple variables, so let us consider the term as a x power n, y power m, and z power some p. So now degree of this term is n plus m plus p. So we have to add all the exponents of the variables. So the sum of the exponents of the variables is that degree. Okay, degree of that particular term. Degree of a polynomial is the largest degree of any one of the terms with non-zero coefficients. Okay, for example, here we are considering a monomial itself. That means a polynomial with single term. Don't get confused. Single variable is different and single term is different. Single variable means just we are in all the terms x will be the only variable. But monomial means only one term. This is also a term, this is also a term. Okay, don't get confused. So for example, we are having a big polynomial like an x power n plus a n minus 1 x power n minus 1 plus and so on a naught. So here the exponent is getting decreased. So now what does degree in this polynomial means? The degree is the exponent which is the highest one. That means largest degree of any one term. Here we are having a n x power 1 as a term, a n minus 1 x power n minus 1 as a term, and so on up to a naught. These are the different terms in this polynomial. So the highest degree of a polynomial with non-zero coefficient. Here a n must be non-zero. That means it can be any value apart from 0. Then it is termed to be the degree. For example, here we are given many examples. Let's look into this. 3x square plus 2. Let's take this as an example. Here, this is one term. This is a term, and this is also a term. Here, the degree of this term is 0 as there is no variable. Here, degree of this term is 2. So now in this whole expression, highest degree is 2. So the degree of this polynomial will be 2. This is how you have to decide the degree. Okay. And last point, degree of 0 polynomial is not defined. Remember this point. Degree of a 0 polynomial is not defined. What is a 0 polynomial? A 0 polynomial is a polynomial which contains only 0 as the term. Okay, if the polynomial is having only 0 as the term, then it is defined to be a 0 polynomial. So degree of that polynomial is not defined. So here we have some classification of polynomials based on degree. A constant polynomial, linear, quadratic, cubic, and quartic. See the difference. Quadratic and quartic both are different. Okay, this you can also pronounce it as a biquadratic term. This can also be termed as a biquadratic polynomial or a quartic polynomial. Anything is fine. So what is a constant polynomial? That means that it is having only constant terms. Okay, the polynomial which is having only a constant term is known as constant polynomial. Then coming to linear polynomial. Linear polynomial means the polynomial with degree 1. See here the highest degree is 1 itself. So that is a linear polynomial. Similarly, the quadratic polynomial means the polynomial with degree 2. Here be careful, we are having two different terms, 4xy plus 2. That means the degree of this term is, this is 1, this is 1. So 1 plus 1, 2. Okay, we have to add the degree exponents of these two variables. Okay, that's why this is a quadratic polynomial. Same, this is a cubic polynomial with a degree 3. Cubic polynomial means the polynomial with degree 3. Okay, quartic or biquadratic polynomial means the highest exponent or the highest degree of all the terms is 4. So this is a classification based on degree of the polynomial. Okay, now let's discuss algebra of a polynomial. So we perform some operations on numbers like addition, subtraction, multiplication and division, right? So we can perform all these algebraic operations all on a polynomial also, on two polynomials also. So now let's see how do we perform addition, subtraction, multiplication and division on polynomials. Okay, the first example, p of x is equal to x power x square plus 4x plus 4 and q of x is equal to 10. So now adding these two, p of x plus q of x, x square plus 4x plus 4 plus 10. See here, this term is one polynomial expression and this is one polynomial expression, right? In the polynomial q of x, there is no x square term and there is no x term, right? We are just having the constant term. So while performing the addition, we have to add the terms with same exponential power. That means here if you are having x square, we have to add this x square with the x square term in the other polynomial. So as we are not having the x square polynomial in this, so we will not add anything. This x square will remain as x square itself. And coming to the 4x term, similarly we have to add this 4x with the x term in the second polynomial. Here we are in the second polynomial, there is no x term, so this 4x will remain the same, nothing to add. And coming to the constant term, here the constant term is 4. We have to add this constant term with the constant term in the second polynomial. Okay, here the constant term is 10. That means 4 plus 10, that is 14. So the resulting polynomial is x square plus 4x plus 14. Similarly here, in this polynomial we are having x power 4 and 4x. But in the second polynomial we are having x cube and 1. Here in the second polynomial there is no x power 4 term. That means the x power 4 will remain the same. And there is no x term also. That means it will remain as 4x. So addition of this second polynomial will give you these two polynomials, will give you x power 4 plus 4x plus x cube plus 1. Okay, I hope you understand. So now let's discuss the other example also. Let's see in the previous slide ones. X cube plus 2x, p of x is equal to x cube plus 2x square plus x and x square plus 2x plus 2 plus 2. Q of x is x square plus x plus 2. Okay, so now we are given these two polynomials. Let me write it more clear. These two polynomials were given to perform addition. Okay, so now let's discuss. In first polynomial we are having x cube, but there is no x cube term in the second polynomial, so it will remain the same. And the second term is x square. So here we are having 2x square. In the q of x polynomial also we are having a term x square. So we will add x square also. And next here we are having a constant term, and similarly we are having a constant term in q of x also. And finally we are left over with x, so we'll add x also. So the resultant polynomial is x cube plus 3x square plus 4 plus x. So to write in the standard form, we have to rearrange the terms such that the power will be in the decreasing order. That means x cube term first, x square plus term next, x power 1 term and x power 0 term. Okay, and to just give you a clarification, I wrote x power 0. Okay, This is how we add two polynomials. Okay. Next, subtraction of polynomials. Subtraction of polynomials is similar to addition. There in the addition we will add the similar terms, and here we subtract the similar terms. So let's see an example here. We are given the same examples as before. So now x square plus 4x plus 4 and 10. So this can be written as x square plus 4x plus 4 minus 10. See here, we are in the second polynomial, we are having no x square term. So we will not subtract x square term with, there is no subtraction required for this x square term. So we'll write it as the same. And here the x term. Here in the second polynomial there is no x term. So this will also remain same. No subtraction is performed. And the last term is a constant term. Here we are having a constant term, and this here also we are having a constant term. So 4 minus 10, that is x square plus 4x minus 10. 10 minus 4 is 6. 4 minus 10 is given, so minus 6. This is how we subtract polynomials. So now let's see this example also. X power 4 x cube plus 2x square plus 2x square plus x plus 2. This is p of x and this is q of x. So now if we subtract these two, same. Here there is no x cube term in the qx polynomial, so x cube will remain the same, and x square is there in both the polynomials. That means minus x square plus 2 minus 2 minus x. Remember, here it's not plus, it's minus. It's not plus, it's minus. So the result is x cube plus x square plus 0 minus x. Be careful here whether it is asked p of x minus q of x or q of x minus p of x. Okay, so the signs will be changed accordingly. Be careful which is given first and which is given next. Okay, next, multiplication of polynomials. Here previously we have seen that addition and subtraction are performed on the similar terms only. Okay, but in the multiplication we will multiply each and every term with the in the second polynomial also. For example, see here, x square plus x plus 1 into 2x cube. Okay, so now here we will multiply each term in this polynomial with each term in this polynomial also. So that means we'll multiply x square with 2x cube, x with 2x cube, and also 1 with 2x cube. Okay, that means x square into 2x cube plus 2x cube into x plus 2x cube into 1. That means 2x power is, that is 2x power 5 plus 2x power 4 plus 2x cube. Okay, and let's see the other example also, we'll get more clarity. So here x plus 1 into 2x plus 1. Now we are having two terms in the second one also. How do we multiply this? First we will multiply every term with the first term, and later on we will multiply every term. Okay, let me change the color. Every term with the second term. So if you multiply like this, you will avoid, you can avoid the confusion. Multiply them in a systematic way. So that means x square into 2x plus x square plus x into 2x. So I'm sorry, I'll write it again. First, x square into 2x. X square into 2x. Next, x into 2x. Next, 1 into 2x plus x square into 1 plus x into 1 plus 1 into 1. So, by adding up all these terms, we will get the product. Okay, now let's see this example. P of x and q of x. X square plus x plus 1 into x square plus 2x plus 1. How do we multiply? First, x square with x square into x square plus x square into 2x, x square into 2x plus 1 into 1. Next, x into x square, this is 2. Next, x into 2x plus x into 1. Next, 1 into x square plus 1 into 2x plus 1 into 1. Okay, this is how we multiply. So now by adding all these terms, we will get x power 4 plus 2x cube plus 1 plus x cube plus 2x square plus x square plus 2x plus 1. So now simplifying this further, let me take another color. This is not visible. X power 4 plus x cube term and the x cube term. 3x cube, 2x cube plus x cube is 3x cube, and 2x square and x square. 3x square, x and 2x, 3x plus 1 plus 1, that is 2. So this is the product of these two polynomials. Okay. I think I did a mistake somewhere. Sorry. This is not 1 into 1. This is x into 1. Let me write it properly. X square into 1. Okay. That means we get 4x square. Okay. Here this is x square, not 1. So this is 1. Okay. This is the product of p of x into q of x. See, here we are given a table. The coefficient of the term with degree 0 is 1. Okay. The coefficient of a term with degree 1, that is 3. The coefficient of the term with degree 2 is 4, with degree 3 is again 3, and with degree 4 is 1. Okay, here we are given, this is the clear idea how do we actually multiply the coefficients. Okay, this is how we multiply. Okay, now let's discuss the division of polynomials. Here we are given two polynomials, 3x square plus 4x plus 3, and the other one is x. Okay, here 3x square plus 4x plus 3 is termed as dividend and x is termed as the divisor. Okay, the one on which we are performing the division is dividend, and the term with which we are dividing is termed as the divisor. Okay, so we can write this also as 3x square by x plus 4x by x plus 3 by x. Now by cancelling both x from denominator and numerator, we obtain 3x plus 4 plus 3 by x. Okay. So here 3 is considered as the remainder and 3x plus 4 is the quotient. Okay. This is how we perform division. So now let's discuss this example. X power 4 plus 2x square plus 3x plus 2 divided by x square plus x plus 1. Okay. So this is x square plus 3x plus 2 divided by x square plus x plus 1. So how to approach in such problems? So the basic idea is we have to change the numerator in terms of denominator. That means we have to make some changes, we have to modify the denominator such that we can make it as a we can make the denominator as factor of numerator. So let's see how to do this. Here x power 4. Here what I am doing is I am adding a term x cube and I am subtracting. See, I am adding x cube and subtracting x cube. That means this will give you zero effect. There is no effect on the polynomial equation. So just added x cube and subtracted x cube. Next, I am writing 2x square as x square plus x square, and this 3x plus 2 will remain the same. Okay, divided by x square plus x plus 1. So what I have done is I added a term x cube and x cube and I splitted this 2x square as x square plus x square. So now how can we write this? X power 4 plus x cube plus x square minus x cube plus x square plus 3x plus 2. Am I right? So now here in these three terms, for example, if we take x square as common term, we can write it as x square plus x plus 1. So which is the denominator? That means we change the numerator in such a way that we got a factor. We made the denominator as a factor for this three terms. So this can be written as x square plus x square plus x plus 1 by x square plus x plus 1 plus, see we have to write the remaining terms also, right? X minus x cube plus x square plus 3x plus 1 by x square plus x plus 1. Okay, so now we can cancel these two. Okay, now how do we modify this term? Okay, here we are having minus x cube term. Suppose again we add, let me change the color, we add x cube and we subtract x cube, and the remaining term will be same plus x square, and we split this 3x as x plus 2x, and this one will remain same by x square plus x plus 1. Okay, so now here we can write these two terms separately. Just observe these terms x cube, x square and x. So if we take x common from these terms, we will get again the denominator, right? So let me write this. Let me take an extra slide if possible, or okay, let me write it on a blank screen. X cube minus x cube minus x cube plus x square plus 3x. Okay, wait, let me write it 3x square as x plus 2x plus 2. Am I right? It's 2, not 1. Is everything correct? Wait, let me check it. Yeah, everything is correct. Oh, it's gone. Let me write it again. Plus 2x plus x plus 1. And the denominator is x square plus x plus 1. So now what I told, write these two terms separately and combine these three terms. That will give you, combining those three terms means it is x cube plus x square plus x. Now by taking common x as common term, we'll get x square plus x plus 1 again, right? So now same, here we got the denominator once again. So x square plus x plus 1 by x square plus x plus 1. Again cancelling these two. Plus the remaining. Here we are left over with minus 2x cube and minus 2x cube plus 2x plus 1 divided by x cube plus x plus 1. Okay, that means here in previously we are having x square and now we got x and now we got this term. So we have to simplify this term further. Okay, now again similarly we have got this term. Sorry, this is x square. So now what else we can do here? So we can split this 2x as x plus x, right? And if required we can add an x square term and we can subtract an x square term. So in such way, continuously modifying the numerator will give us the solution easily. Okay, the main key idea here is we have to try to write numerator in terms of denominator such that we can cancel it as a factor. Okay, next, the division algorithm. I have said you previously what is dividend and what is divisor. So here the term on which we are performing this division operation is termed as dividend and the term with which we are dividing is divisor, and the coefficient and the remainder. See here in the previous example we got x square plus x plus something. Okay, this is the quotient and the remainder. I'm sorry, I wrote a mistake. Basically the division algorithm is divisor by dividend by divisor is equal to quotient plus, wait, I'm sorry, I'm messing it up completely. Dividend by divisor is equal to quotient plus remainder by divisor. Okay, so this is the term on which we are performing the division, and this is the term with which we are dividing. This is the quotient. That means we have seen before in this example you got x square plus x. That is the quotient and the remainder. See, to explain you more clearly, we have considered let's see an example. We'll consider. See, for example, x square plus x cube plus x square plus 1 by x. So now this is dividend, this x is divisor. So now this can be written as x square plus x plus 1 by x, right? So now this is the quotient and this is the remainder. 1 is the remainder here. What is the remainder? 1, as the x is the divisor. 1 is the remainder, x square plus is the quotient, dividend is x cube plus x square plus 1, and x is the divisor. Okay, hope you understood the division algorithm. Next, so now coming to the graphs. So this is one of the important part of the polynomial functions, characterization of graphs of a polynomial function. So we have some the basic factors for a polynomial function. That means by seeing the graph we can say whether this is a polynomial or polynomial function's graph or not. To determine that, we have some certain properties of polynomial functions. Those are: the polynomial function of second degree or higher have a graph with no sharp corners. That means the graphs are smooth curves. So see here in the given picture, here we are having a sharp corner. So this is not a polynomial graph. So all the turns we have are smooth curves. Okay, and the polynomial graph is always continuous. There will be no break. So for example, if you are having a graph like this, okay, we are having a graph like this. Here there is a break. Let me use another color. Here there is a break. So this is not a polynomial graph. So the major points are there will be no sharp corners and there will be no breaks. It is a continuous graph with smooth curves. So zeros of the polynomial. What are zeros of the polynomial? See, for example, we are having an equation of polynomial x cube plus x square plus x plus 1. So 0 of the polynomial means the value of x for which the polynomial f of x will be 0. That means here we will substitute some value in place of x. So the value with which this term will become 0 is termed as 0 of the polynomial. So here we can have multiple zeros for a polynomial, not only a single 0. See, here we have some different methods: the greatest common factor, grouping, trinomial factoring, polynomial in factor term, and you can use some technological equipment also to find out the zeros of a polynomial function. So now the next one is the x-intercept of a polynomial function by factoring. See, if the x-intercept is nothing but the 0, okay, it is the value of x for which the f of x term will become 0. That is the x-intercept alone. So now how do we find that x-intercept? By factoring. Here we are given an example: x power 6 minus 8x power 4 plus 16x square, right? So here we can take x square as a common term and we can write x power 4 minus 8x square plus 16. So this is x power, not x power, it's x square into x square minus 4 whole square. Okay, so in this way we have to reduce the polynomial function such that we can factorize them easily. So here when we equate it to 0, what are the possibilities? There are two possibilities: x square can be equal to 0 or x square minus 4 term can be equal to 0. So similarly we have to factorize. That means factorizing means simply we have to reduce the term, reducing, taking the things common, turning them into perfect square. So these are the methods usually we use to factorize a polynomial. So now let's see some examples. Okay, x cube minus 4x square minus 3x plus 12. So this is the example, minus 4x square minus 3x plus 12. Okay, so now how do we factorize this? Observe first two terms. Here if we take x square common, that will be x minus 4. And observe the next two terms. From here if we take minus 3 as a common term, then it can be x minus 4. So now from these two terms, if we take x minus 4 as a common term, we can write it as x minus 4 into x square minus 3. So this should be equal to 0. So now we have simplified the equation. So now it is easy to find for which value of x the f of x will become 0. Simply the two possibilities are x minus 4 can be equal to 0. That means x is equal to 4. Or x square minus 3 can be equal to 0. That means x is equal to plus or minus root 3. So these two are the solutions, zeros or the x-intercepts for the polynomial function f of x. Okay. So there are many methods to find these zeros. Okay. Every example will give you a unique process to how to factorize this. So the best way to the best way to solve is you have to get the experience from the practice. Then itself you can get different ideas on spot. Okay, because we cannot assure that only this kind of example will be asked or only the previous model will be asked. There will be different infinite number of examples. So by practicing different models itself, we will be able to solve in the exam time. Okay, now the next question is g of x. Here this is much more easy. It's already given in the simplified form. So far we have discussed the x-intercept. What is x-intercept? The value of x for which the polynomial equation will be equal to 0. That means x minus 1 is equal to whole square is equal to 0. That means x minus 1 is equal to 0. That is x equal to 1. And the other one is x plus 3 is equal to 0. That means x is equal to minus 3. Then what about y-intercept? Okay, y-intercept means we will substitute x value as 0. This is in case of y-intercept. Okay, the value obtained by substituting x as 0 will be the y-intercept. Here substituting x as 0 will get minus 1 into 3. That means it is minus 3. So the y-intercept is minus 3. Okay, be careful. If x-intercept is asked, we have to find the value of x for which the polynomial equation will become 0. If we are asked to find the y-intercept, we have to substitute 0 in place of x and find the value. Okay. Next, identification of zeros and their multiplicities. So we have so far discussed how to identify zeros just by reducing the polynomial equation. Okay, by taking the factors common or by simplifying it as a perfect square. In many ways we can find the zeros, and now have to find out the zeros and the multiplicities. Okay, the graphs behave differently at various x-intercepts. So here, as we have discussed before, a polynomial equation can have different zeros. That means there can be 3 zeros, there can be 2 zeros, or there can be only 1 zero. Okay, at each zero the behavior of the graph will be different. Okay, sometimes the graph will cross. That crossing means, see for example, this is called crossing. See here, the graph is crossing the x-axis, and sometimes it will bounce off. Bounce off means just like this. Okay, it will be touching, but it will not cut the x-axis. See, if this is passing like this, that means it is crossing. This is crossing. this is bouncing off. It will touch, but it will not cut the x-axis. Okay, so how do we determine whether the graph will cut the x-axis or whether the graph will bounce at that point, at that x-intercept? So that can be determined by finding the multiplicities. Okay, let's see here, given a polynomial of degree n, if the graph touches x-axis and bounces off, that means there is a 0 with even multiplicity. Okay, that means, for example, we are given some random graph like this. This is a random graph. Okay, graph may or may not look like this. It's just a random graph. Okay, so now let's take another color. Here the graph touches the x-axis and bounces off. See here, at this point the graph is touching and bouncing off. Okay, that means this is a 0 with even multiplicity. Okay, and next, if graph crosses at x-axis, it is a 0 with odd multiplicity. See here, this point and this point and this point. In these 3 points, the graph is cutting the x-axis. That means these 3 points are zeros with odd multiplicities. Okay, if the polynomial, if a 0 is having even multiplicity, then the graph will bounce at that point, will bounce off the axis at that point. If the graph is cutting the x-axis at that point, that means the graph, the 0 is with even odd multiplicity. Okay, so here we can derive the conclusion in either way. See here, we are given a graph. So here we are seeing the we are having 4 points where the graph is touching the x-axis. So here we are having 3 points which are cutting and 1 point which is just one point at which the graph is bouncing off, right? So from the graph we can determine whether the zeros are having even or odd multiplicities. Similarly, if we are given the graph, if we are given the zeros are with odd multiplicities, then while drawing the graph we will get an idea whether at that point the graph will cut or the point should bounce off. Okay, so from the graph we can determine the multiplicity, or from the multiplicity we can determine the graph. Okay, we can draw the conclusions from the either side. Okay, these are some important points to remember. Okay, now so from the graph we can determine whether the multiplicity is even or odd. Okay, but how do we say that multiplicity is 1 or multiplicity 3 or 2, 4? How do we determine this? We have a property called the sum, the sum of all the multiplicities is not greater than n, where n is the degree of the polynomial. Okay, n is degree of the polynomial. So the sum of all the multiplicities, whether it may be odd or whether it may be even, the sum of these multiplicities will always be less than or equal to n, but not greater than n. So from that we can check the possible multiplicities. Okay, now let's discuss an important example. So here we are given a graph, and using the graph we have to find the multiplicities of the 0. And we are given one more important point is that degree of this function is 6. Okay, so from the graph we can see that -2, 0 and 2. -2, 0 and 2 are the zeros. So now we have to find out the multiplicities. Okay, here as we have discussed before, if the graph cuts the x-axis, then the multiplicity is odd. If the graph bounces off at the x-axis, then the multiplicity is even, right? So from the graph, given graph, at -2 the graph is crossing the x-axis, minus 2 as well as 2, and at 0 it is bouncing off. Okay, that means the multiplicity is odd for minus 2 and 2, and it is even for 0. Okay, and we are given one more condition, that degree is 6. So we can, as we have seen before, we can think that the multiplicities of minus 2, 2 and 0, the sum of all these multiplicities is less than or equal to 6. Okay, so now from this condition and from these odd and even conditions, we can get the multiplicities of these three zeros. See here, the multiplicity of 0 can be either 0 or 2 or 4. And here the multiplicity of minus 2 can be 1 or 3 or 5. And here the multiplicity of 2 can be 1 or 3 or 5. Am I right? See here, let me see, I'm clearing this. Here if you observe at minus 2, the graph is almost a straight line. Okay? That means the multiplicity at minus 2 is 1. And when you observe at 2, it is showing the cubical nature. That means the graph, that multiplicity is 3. So now here we have got the multiplicities of 2 and minus 2. So sum of these two multiplicities is 4. So now as we have seen this condition, the sum of the multiplicities must be less than or equal to 6. So the multiplicity of 0 can be only 2. That is the only possible value. Okay, this is how you have to determine the degrees from the graph and from the degree of the given equation. Not degrees, multiplicities of zeros from the given graph and degree. Okay. Now next one, and behavior of polynomials. So now so far we have discussed how the graph of the polynomial will look like at x-axis. Either it is cutting the x-axis, it's bouncing off the x-axis. So now what about the end behavior? That means when x is tending to infinity and x is tending to minus infinity. These two are the end points in general considered. These two are considered to be the endpoints of polynomials. As polynomials are continuous, there is no limit for polynomials. We can substitute any value. So we consider infinity and minus infinity as the endpoints. So now how the graph will behave at these particular points. Okay, that is what we are going to discuss, and that is called the end behavior of the polynomial. Okay, now here we have some 4 cases. An is the coefficient of leading term. Okay, remember this will play a major role, coefficient of leading term. And whereas here even degree, that means the exponent, the highest exponent. We have discussed what is the degree previously, right? Okay, so the nature of the nature of the polynomial will be decided by the coefficient of leading term and the exponent of the highest, the degree of the polynomial. So we have 4 cases here. The coefficient of leading term is positive. In that condition, the degree may be even or the degree may be odd. And the other thing is, the coefficient of the leading term can be less than 0 and the degree can be even or odd. So these are the 4 cases that we are going to deal with. Okay. First thing, even degree. Okay, let me take an example of a polynomial here. An x power n plus and so an minus 1 x power n plus and so on plus a naught. Okay, so now here this is the leading term. See, an is the coefficient of leading term, whereas the degree is n here. Okay, this is n minus 1. Okay, so Here, for example, an is greater than 0. In that case, we have two situations. N is even, n is odd. Okay. Here, in the case where n is even, either we substitute x equal to infinity or x as minus infinity, f of x will always tend to infinity. Remember here, the n behavior will always depend on the leading term itself. Okay, so here that's why we are just discussing about the coefficient of the leading term and the degree. Okay, only this term will decide how the n behavior of the polynomial is going to be. So here, if we substitute x, for example, if n is even, let us say n is equal to 6. Anything, either it may be a negative number or positive number. If we substitute, if we write it to the power of an even number, then that will definitely result a even number itself, right? So infinity power 6, or minus infinity power 6, both will lead up plus infinity, right? Whereas if the degree is odd, then for positive infinity it will tend to positive infinity, and for negative infinity it will tend to negative infinity. So this is the case when the leading coefficient is greater than 0. Okay, now the next case is when the coefficient is less than 0. Okay, the polynomial, let me write it again, an minus 1, x power n minus 1, and so on up to a naught. Okay, so now this is the polynomial we have, and I have said before, this leading term will decide the behavior. Same, an is the leading term, n is the degree. So here an is less than 0. Okay, that means and the other one is, for example, now let us take an is less than 0 and n is even. Okay, this is the case we have. So here I told this is a negative term, that means this x power n is having a negative term with it already. Okay, the negative sign is already present. So now as far as only x power n is concerned, if we take, like, if you are having n as even, then for any value of x, this x power n value will be even. For any value of x, the number will be positive. It's not even. As far as x power n is concerned, when n is an even number, for any value of x, it might be positive value or it might be a negative value, this x power n will be a positive value. So here we are having a negative sign already. So this negative sign multiplied this by this positive sign will lead to a negative value. That's why here when x is tending to infinity, f of x will tend to minus infinity. So now, and same as, here x is tending to minus infinity and f of x also will tend to minus infinity. Okay, no matter x tending to infinity or minus infinity, when the degree is even and the coefficient is less than 0, f of x will always tend to minus infinity. So now coming to the odd degree. Okay, so now here this negative sign is already present, and coming to this x power n, as far as this is concerned, we have discussed before, right? If n is odd, for positive value the result is positive, for negative value the result is negative, right? So here if x is positive, if x is positive, then this will be positive. So here we are already having a minus sign with it, that means this will be a negative value. Okay, if x is a negative value, this x power n will be a negative value. Here we are already having a negative sign before, so minus into minus will always lead you a positive term, positive value. So that's why here when the degree is odd and the coefficient is less than 0, if x is tending to plus infinity, f of x will tend to minus infinity. If x is tending to minus infinity, f of x will tend to plus infinity. Okay? Remember here, just 2 points you have to remember. The end behavior is always decided by the leading term. Okay? And the 2 conditions that you have to check are whether the the coefficient of leading term is positive or negative, and the degree of the polynomial is even or odd. Okay? So these are the 4 conditions of the end behavior of a polynomial. Okay? Okay, now let's discuss an important topic, turning point. So here we are given a polynomial equation. So how we have to determine how many turning points are there for that polynomial graph. Okay, this is an important topic. Here let's see with some examples. Here given f of x is equal to 4x power 5 minus x cube minus 3x square plus 1. Be careful while arranging them in ascending order of their degree. Ascending order of the exponents. See here 4x power 5 is given after the x cube term. You have to be very careful while writing it. Okay? And while discussing the turning points, we have an important note here. The number of turning points are always less than the degree of the polynomial. And one more thing is the maximum possible turning points for a polynomial equation are degree is equal to degree minus 1. So this is really an important point to remember while doing the problems based on this turning point. This is really helpful. So now suppose we are given a polynomial equation here. How do we actually determine the turning points? Okay. So here we have 2 steps. The first derivative step and the second derivative method. First derivative and second derivative methods are used to determine these turning points. Firstly, we have to check the points where the f dash of x, the first derivative of the polynomial equations, are becoming 0. Okay, this derivative must be equal to 0. See, look here, 5x power 4 minus 3x cube minus 6x. So this is the differentiation, first order derivative for this f of x. Okay, this must be equal to 0. So now taking x common, it will be 5x cube minus 3x minus 6. Sorry, it's not 5, it's 20. I'm sorry, it's 20 equal to 0. So now here we have the possibility that x can be 0. So 0 value, if we substitute x equal to 0, then this equation will be 0. And the other option is to make this as 0. So the turning points are the local extremas. Okay, there will, for a polynomial equation, when we sketch the graph of a polynomial equation, definitely there will be a turning point at the local extrema. It might be the local maxima or it might be the local minima. So here we have a condition that the local minima and local maxima both are the points where f dash of x will be equal to 0. So to determine whether the points are local, the given point is local maxima or minima, we have 2 conditions. First thing is f dash of x must be 0, and if f double dash of x is greater than 0, then that point is local minima. If f double dash of x is less than 0, it is local maxima. Okay, these two are considered to be these two together are considered to be local extremas. Okay, so here the common condition for this f local minima and local maxima is f dash of x is equal to 0. Okay, so in the previous case here x can be 0, or the zeros of the equation 20x cubed minus 3x minus 6 are also considered as are the points where the polynomial is having a turning point. Okay, and we can sketch the graph for this polynomial, okay, by checking the points, by plotting the graph also we can see where is the turning point. Okay, so in today's class we have discussed about polynomials, what is the degree of the polynomial, how to find zeros, how to find their multiplicities, the end behavior and the turning points. Hope you understood and enjoyed the session. Thank you so much.